Hello everybody to the last day of our conference. I hope you enjoyed your time so far. Last but not least, we have now a very interesting talk by Professor Carola Schönlieb. She made her PhD in 2009 in Cambridge. She is currently professor in Cambridge and also head of the image analysis group in Cambridge. She actually got many honors, among them the Whitehead Prize of the London Mathematical Society and the Calderon Prize of the Inverse Problems Community. And with all the things nowadays going on, it is a wonderful thing to have a talk on the last day by somebody whose research interests are in the use of variational methods, PDEs, and machine learning in image analysis, in particular also bioimaging. So without further ado, I hope you can all enjoy a talk now on deep learning and neural networks and enjoy your time on the last day of this conference. Please, Schönlieb.
Okay, thank you so much. Thank you for the really kind introduction. Can I have the slides, please? Perfect, okay. So, the title of the talk is Structure Preserving Deep Learning, and I chose this as a topic that is very timely. So deep learning nowadays is a very important tool, is a very important component of our everyday life, but also going into science and technology and indeed also research related to various different kinds of questions. And the structure preserving looking glass onto deep learning is, I believe, a very interesting one for analysts like ourselves, since the framework of partial differential equations, dynamical systems, functional analysis is one very important entry point into imposing provable structure into neural networks. And why this is important and why this could be useful, I'll also aim to reveal in this presentation. So this is a topic that I have been very passionate and very interested in for almost the last 10 years or so. So I hope I'll offer you some broader perspective onto this topic. Of course, it will be colored by the kind of things that we have been doing there, which are in particular related to using neural networks to solve inverse problems and using neural networks to solve PDEs. Okay, so a bit of background. So Uwe mentioned that I had the Cambridge Image Analysis Group in Cambridge, also in short the CIA of Cambridge. So we are a very large group of people, postdocs and PhD students, working on a variety of different topics that I'll show you in a moment. Let me just pause here and really thank all the people in the group for the wonderful things that they're doing. Everything that I'm going to present to you is really, wouldn't be there without having very fruitful and interesting discussions with them and also doing the research together. And also let me thank all the sponsors of the research that we are doing. In particular, for this talk, I want to thank EPSRC, since they have founded a large grant over the last 4 years for us on the mathematical foundations of deep learning of neural networks. So, what do we do? Maybe just to say, my own background is in PDEs and variational models. I started out my PhD looking at the Cahn-Hilliard equation and at the stationary states equation. And at the time, actually, so how did I get into imaging? At the time, well, PDEs have already started to be useful in image processing and image analysis before my time. But at the time when I looked at the Canhilliard equation has also found its use in work of Andrea Bertozzi from UCLA in image restoration. So using the Canhilliard equation as an interpolator to close gaps in images. And that was super fascinating for me, and it coincided also with an interesting collaboration opportunity in Vienna. I did my PhD, partially in Vienna. In Vienna, where there was a collaborative opportunity to work with actual art restorators on who were restoring a fresco in the city center of Vienna called the Neidhardt frescoes. And they wanted to have some digital mock-up of what the restoration could look like. So this is where all of this, what you see here, started. So now what we do is we develop mathematical methods and underlying theory based on, so the mathematical toolkit being PDEs, variational models. Optimization, of course, pops up once you discretize these models. And lately, for the last 10 years or so, also machine learning increasingly to solve a wide range of, does this pointer work? Should it work or not? I don't see it. Do you see it? Do you see it? No. Should it work? Did it work yesterday? It didn't. It did, okay, well. Left column, these are the kind of mathematical problems that the group is working on. So in the realm of solving inverse problems in imaging, image analysis and image processing problems, with a few concrete examples here. So I would say you can classify them into two groups. One is getting the best image out of imperfect, usually imperfect, noisy measurements that you take in applications. And the other one is quantification based on imaging data that, again, is robust to noise and corruptions and so on and so forth. And usually a lot of what is happening here on the left-hand side is directly motivated and indeed in collaboration with people who are actually measuring this data, who are actually using this data in their research. And since images are in a lot of places, the kind of collaborations we have are also very diverse. So ranging from the biomedical domain to environmental sensing to, as I mentioned before, art and cultural heritage. Okay. So before we actually go into structure-preserving deep learning, I just thought, since it's Friday morning, and also because I love this video that I'm going to show you now, I'm going to show you this video, which has been actually produced as an outreach material to explain why mathematics is important in everyday life, exemplified for imaging. And I think it nicely shows, it gives you some kind of insight into the problems that we are thinking about. So without further ado, let me just show this video and then we'll continue.
Hey, Carola.
Hi, Samu.
Hey, you know how to remove things from photographs, right?
That's right.
Can we try?
Sure.
Can you make the coke disappear?
Okay. Watch it.
All right, pretty good. I think I can still see something.
Yeah, that was harmonic imprinting.
Okay.
We can try total variation imprinting.
All right.
Okay.
Oh, pretty cool.
Ah, isn't it?
All right. Can we try some more stuff?
Yeah, that would be fun.
All right.
Let's do
go
it.
Try it. That is all pretty cool.
Yeah, that's the power of applied mathematics.
But can inpainting make us disappear?
Sure.
Okay, thank you. Right, so this gives you an impression of what people like myself are kind of doing, are thinking about all day long, basically, is really how to model images, how to model the connection of images to the data in a way that is both qualitatively truthful to the structures that we see in images, as well as truthful to the data that we measure, and should be computationally solvable in a scalable way because imaging data is large. So this is in a nutshell what we are doing. Deep learning entered this domain, of course, because it's a natural use case for a model like a neural network that is very capable to adapting to data that it is trained on, and to a domain where lots of data, lots of imaging data, digital images are available. And so this is really the entry point, was also the entry point for us to think how can we use neural networks in contexts like this to make the approaches that you just saw in this video better, qualitatively better. So even in the best ones, you know, that we showed as the last iteration of the methods that you saw, you still saw shortcomings, and so this is where the idea of making these approaches more adaptive to imaging data comes in. And from experience, modeling images with partial differential equations is very challenging to do this in a way that really preserves all the fine scale details and so on and so forth. Now the structure that is being imposed in the structure preserving deep learning context comes in as an additional component in contexts where actually having some provable guarantees about the images that we reconstruct is important. So that wouldn't be the use case maybe for, you know, playing around with images like we did in this video, but it is the case when you use approaches like this in the medical domain, in the scientific domain, when you use imaging data to do research, or indeed in critical applications like autonomous driving or something like this. Not that I'm working in this topic. I'm more in the scientific medical imaging domain, but you can imagine here having a structure in neural networks when you use machine learning to solve these tasks is very important. Okay, so structure preserving deep learning refers commonly to deep learning with structural constraints, and these could appear in various different shapes and forms. Here I'll just have a few examples of where they appear, again colored by the kind of things that we are working on in the group. But I think they're fairly representative. So one is when you use deep learning to solve inverse problems. So inverse problems allude or denote a range of mathematical problems where you're measuring something that is here mimicked for the application of X-ray computed tomography that will accompany us, by the way, throughout the talk. This will be our prime example, X-ray CT. So you measure something that you see here pictured on the right. It's called a sinogram. These are X-ray projections of usually a 3D object that you image. Here it's just simulated in 2 dimensions. And what you're actually interested in is to reveal the object that you see on the left, which is, in this case, a 2D slice of an abdominal scan, an abdominal CT scan. You want to compute this left image from the data on the right. And the capital T that you see on the very left is the process that, also in inverse problems called the forward operator, the operator that takes the image towards the data on the right. Now, while usually this forward process is a well-posed problem, the typical inverse problem related to this, which is what is practically appearing, because what you measure is what you have on the right. This is what the machine, the X-ray machine, gives out. And to go back to the image that you see on the left is typically an ill-posed problem because of properties of the forward operator, because there is no continuous inverse to capital T. And that, of course, the ill-posedness often also shows in the solutions that you compute of this inverse problem because of the noise that you have in the data. So in particular, if continuous dependency of your solution on the data that you measured, if that fails, you have a problem if there is noise. So deep learning entered that, as I said, as a way to model how images look, also in this medical domain, in a better way, and hence make solutions to these inverse problems better. We will talk more about this in a moment, so I'll stop here. Other domains where deep learning appeared is for solving or also discovering partial differential equations. This is actually a bit of a misleading example that you see here on top. I've just chosen this because this is the latest thing that we did in this context. Here, we are not using a neural network to solve a PDE, but we are using a neural network to create an adaptive mesh to solve the PDE with finite elements afterwards. So there are various ways how neural networks have entered the numerical solution of PDEs, let's say, in general. In particular, for PDEs that are defined in high dimensions, and in particular also in applications where you want a fast and maybe not so accurate solution to your differential equation. So this is really about using deep learning to solve mathematical problems. Now the last one that is here on the bottom is where it's a little bit the other way around, where mathematics is used to make deep learning in various different applications better in terms of making the deep learning model robust or stable, as I call it here, making it more efficient either to train or to apply, and maybe also more accurate. And this can range, again, from people thinking about, efficient optimization algorithms to train neural networks, all the way to architectures that make the training more efficient, or to architectures that we know approximate a certain class of functions, or that have, some other mathematical properties that are desirable, for instance, for stability, like one-Lipschitzness, which is what we are also going to touch later on. So this is more or less where structure preservation in different shapes and form appears for deep learning. Now what I want to do is I want to in particular zoom into structure preservation in the context of inverse problems. Where it appears and why this is interesting to to investigate in the context of inverse problems, the structure-preserving deep learning paradigm. Now, structure-preserving deep learning for inverse problems, but actually more generally, when mathematics and deep learning meet, can have two different connotations. I'm wanting to use this pointer, but I can't, sorry. The first one is you have a mathematical model, like for instance, here on top I have a variational regularization approach for solving an inverse problem. And I want to use deep learning to enhance this mathematical model, okay? The mathematical model that I'm going to use and that I'm going to analyze in the end will be a variational model, but there will be a neural network somewhere, and the art of modeling this, or the point where structure is imposed in the neural network is how to model the neural network such that you still have a well-behaved variational problem, whatever well-behaved means. Well-posed, efficiently computationally solvable, and so on. The other direction is when you have a model that is the neural network itself. So you start with a neural network to solve, let's say, the inverse problem. And you impose mathematical structure into the neural network. Oh, thank you. Great. No, okay, perfect. Danke, Uwe. Thank you. Okay. And you want to impose structure into the neural network to, for instance, achieve, like in this case, convergence to a fixed point or something like this, right? Of your now iterative procedure to solve the inverse problem that is now based on iterating through a neural network. And hence you want to know that if you iterate, you'll arrive at some point at a solution to the equation that you set out to solve. So the constraints that arise in this context are quite diverse. I mentioned one Lipschitzness before. Convexity, of course, is a nice property to have when you solve a variational problem in the end. In particular, if your inverse problem is linked to some physics-based dynamics and physics-based phenomena, various different things could appear: mass, volume, positivity preservation, and also taking into account properties of the inverse problem of the forward operator itself, might make sense to impose into a neural network solution that solves this inverse problem, like, for instance, a range or null space condition. So now I want to zoom into the first topic, and in particular talk about what I've written here, adversarial regularizers, which is something we have been working on for quite a few years now, which is the following. So just one very brief slide about variational regularization. Variational regularization, which is this minimization problem that you've seen on this slide here, appears as a way to solve an inverse problem. In particular, in the case when your forward operator is linear, this is also applied in the nonlinear case. But of course, analysis in this setting is much more challenging. Let's stick therefore to the linear case. So you have a linear forward operator capital T between two, now at the moment, generic function spaces. Usually how people are approaching to model solutions to inverse problems, even though in the end you solve a discrete problem, usually people start in infinite dimensions. So you have two infinite dimensional function spaces where you put all your modeling knowledge and capacity into to say something about the data and something about the type of images you want to compute. And then once you have the model that solves this problem, you discretize it at some point. Okay. So now, as I said before, these problems are typically ill-posed in applications. So one way around this ill-posedness is to turn to a different problem, which is the variational regularization approach, where you complement this forward model here for the data with knowledge about the type of solutions that you want to compute from your measurements. Why? And this is usually modeled, at least in the function analytic setting, in terms of a regularization term within an optimization problem, which captures both the properties of the data and the properties of the solution. Okay? So you have a so-called data discrepancy term in this energy minimization problem that quantifies how far your measurements are from your forward model. Okay, so imagine this could just be here like a least squares fit. This, how everything here is modeled, is mostly coming from statistics. You can interpret, by the way, for those who are also statistically inclined, this variational regularization approach also as a maximum a posteriori estimator in a Bayesian setting for computing computing possible solutions that can explain this data Y. So, in particular, the choice of in this case the norm here, but could also be any discrepancy. For instance, Kullback-Leibler also appears as a typical discrepancy for the type of inverse problem that appear in applications. It really is determined by the distribution of the data. So L2 squared just often appears because the normal distribution is a very good proxy for lots of things. Kullback-Leibler, for instance, appears for Poisson distributed data. Okay, but I'm deviating too much. So this is the model, this is data discrepancy, this is the regularization term. Now the regularization term makes the problem well posed by introducing prior knowledge about what I want to solve it for. This you can think of, again in the function analytic setting, is basically reducing the solution space to a space in which my model is now stably invertible. Okay. So how does what's typical examples? So the typical Tikhonov type of regularization is an L2 or an H1 seminorm type of term here. In image processing, what has really been extremely successful are so-called sparsity promoting regularizers or non-smooth regularization procedures that model images by saying there is a way to describe this image in a very efficient, meaning sparse way, in a representation that fits an image. And the total variation appears, which in finite dimensions you can interpret as an L1 norm of the gradient of U, as a way to say the gradient of U should be sparse, meaning that most of the image can be explained by something where the image intensity function is constant, and there are just a few places, and these are the important places that we want to preserve, where the image is discontinuous, where you have jumps in your image intensity function, which are when the gradient, which are the places where the gradient is non-zero, or actually in the continuum infinity, of course. Now, L1 appears as a convex relaxation of this sparsity constraint, so it is indeed imposing sparsity. When you go back to the total variation directly, this you can also explain this in infinite dimensions, that this is also a nice thing for images because your image function U that you compute with such a regularization term can actually represent discontinuities. So your solutions will live in the function space of bounded variation functions, which is a nice space for images, it turns out. So, right. Now, this is all good and well so far, and a lot of people have thought about how to model this regularization term, and you have seen some examples in the video. So total variation in painting, you've seen how this would look if you use it as an interpolator, where you're, in painting, by the way, your capital T is just a projection operator onto the domain on which the image is known. But there are also limitations, of course, to these type of models, in that they are very generalistic. They apply to various different settings. I can apply them to medical images. I can apply them to digital versions of frescoes. But this generality also has the downside of not being very accurate for specific things that we see in these images. In particular, thinking about very fine scale features that I have in images, and very specific features that I might have in a medical image and that I don't have in a fresco, and the other way around. So this is where the idea of learning this regularization term, learning a prior, comes in, okay? And again, neural networks are a natural choice because they're very capable of modeling, of capturing information from data that could serve as such a prior. And this is a teaser of what you can do with this idea. So here you have 3 different reconstructions based on X-ray CT measurements, so based on these type of measurements that I've shown at the beginning. And all 3 of these reconstructions fit the data that you've measured in exactly the same way. So they're all plausible reconstructions. They just vary in the prior information that you're using to solve the inverse problem, to propose a solution. On the left is what is called filtered back projection. So this is if you have a linear inverse problem, the first thing you could try is to compute the pseudo-inverse solution to your problem, which in the context of X-ray CT is the filtered back projection. Here on the left is a total variation regularized solution. And on the very right is a solution when you replace now the regularizer with a neural network, in particular with a neural network that is trained in this adversarial fashion that we then call the adversarial regularizer, that I will explain now. Okay, so just very quickly again, what we do is we stick to the variational problem and learn this regularizer and see how far we get. Okay? And this idea had several connotations throughout the years that we have worked on it, where we've learned a lot from the things that we didn't do ideally. So it was definitely an iterative scheme also for us to arrive at a framework in which this learning the regularizer it turns out to be meaningful. And so this is the last iteration of it. It's called the learned weakly convex regularizer. So these are still regularizers within this adversarial class, but they have the structure of being weakly convex, and I'll explain this in a moment, which will have some advantages to how we are going to use them. Now, the first thing, if you want to train a regularizer, if you now want to use a neural network as a regularizer, is to think about how do we train it? What's a good objective to actually train this regularizer? What's a good objective, and what's good associated training data to do this? Now, if you look at this variational problem again, in a way, conceptually, what this regularizer should do is it should distinguish between good and bad solutions to this inverse problem. So you want to fit the data, but you want to select the solutions that fit the data that have some certain qualitative properties. And if you do this within such a minimization problem, how the regularizer is doing this is by penalizing the V's that you don't want, meaning that the regularizer for these V's should be large, and to promote the V's that you want, which means the regularizer should be small for these V's, okay? And this is basically how we train it. So now I've more or less told you how we train it. We train it to be large for desirable V's, to be small for desirable V's, and to be large for undesirable V's. And so how do we model these? It very much depends on your application. For X-ray CT, for instance, something that makes sense is to start with the data that you want to solve the inverse problem for. In our case, we aimed for two types of corruptions that we have in the data. One is noise, and the other one is undersampling. So you're not measuring as much, or let's say this, you have an underdetermined problem. It's very easy to create out of this the undesirable examples, right? You just compute reconstructions to some baseline method, like for instance computing the solution to the pseudo-inverse based on this data, which is what we did here. And you do this for a lot of data that you've measured, and you create through this an empirical distribution for an underlying distribution that I call here Pn. So these are the distribution of the undesirable examples. And then for the desirable examples, this again now depends on the application. These should be examples that really contain the type of qualitative structures that you want the regularizer to pick up and learn. Okay, so they should be good enough and close enough to the type of things that you see in your actual application to mimic that. And so again, in X-ray CT, the easiest would be to just use reconstructions from fully sampled, noise-free or very small noise. It will never be noise-free, but very small noise settings. Okay? So these are my desirable examples. And if you don't want to do this with humans, and in this case, actually, we didn't even, go to the limits of this. So hence, we could actually just use clinically available reconstructions, which are usually fully sampled and have relatively low noise. You can also use phantoms, for instance, to do this. If you're worried about X-rays and shooting them onto people. Now, based on this, and then you have another empirical distribution. You again do this for lots of individuals, lots of specimens, and you create an empirical distribution of your underlying distribution PR of desirable examples. Okay, and then you turn everything that I've said into an objective, into a training problem for this regularizer. And here what popped up in a way very naturally, and which also nicely connected to some parallel developments at the time in the context of what is called generative adversarial networks, is to use a loss function, an objective, to train a regularizer that is motivated by the one Wasserstein distance. Okay, so why is this doing what I've said it should do? Well, what it does is it maximizes the regularizer for samples from the undesirable distribution. Okay, this is what I've said we want to do. And it minimizes the regularizer for samples from the desirable distribution. And then I have some one Lipschitz constraint that is also useful later for when you plug it back into the variational problem to have some continuity properties. So this is the continuum model in the background that we use as a motivation. Now we deviate from the one Wasserstein distance. We insert now neural networks, so we don't optimize over all one Lipschitz functions, but we optimize over a certain class, certain type of parameterization of neural networks. And here the structure indeed comes in. Well, the structure already comes in by the one Lipschitz property, but structure also here comes in what else we want from the regularizer. And so here you can do different things, but the one that I will talk about is weak convexity. So we want to model regularizers as weakly convex functions, and I get to this in a moment. This little L2 squared term is basically here for convenience to make sure that everything in the variational problem in the end is coercive, right? If you deviate from convexity, you very easily end up with having something that is not bounded from below anymore. Okay, so then you have a neural network instead of all one Lipschitz functions, and then you insert this into your optimization problem. You turn the one Lipschitz constraint into a penalty term, and that's your training. That's your training problem that you're solving. Nice thing about using a loss function like this for the regularizer in the context of inverse problems is that you don't need your desirable and undesirable examples to be paired, which means they don't need to come from the same underlying object, which is very handy because very often in inverse problems, the data you want to use your inverse problem solution for, you don't have this wonderful solution. If you would have it, then why? So, I mean, why look for a better solution? So having this separated is actually very nice. This is just, I think I've said this already, this is just again the recipe, so let me jump that. Now, one word about the structure that we put onto this regularizer. I said that we converged in a way through several iterations to this weak convexity as a good structure to have. But why is this an iterative process, and why not have convexity, for instance? This would be even better if you think about the mathematical properties of your variation problem. Usually the thing with using a learnable component is, and this is in particular true if you start with a model like a neural network that is extremely capable to adapt to the underlying training data. The thing is, the more structure you impose onto this model, the more you gain stability, but very often in practice you lose performance. You lose adaptivity. And this alludes to one problem, by the way, in structure preserving deep learning in general, which is that there is this trade-off between stability and performance, mainly, I think, by, again, us not being very good in modeling the necessary assumptions that we want from our solutions in the best possible way. Usually we overdo it, we impose too much. Yeah? So this is in particular true for one Lipschitzness, for instance. One Lipschitzness for neural networks is a more or less open problem, how to do this in an accurate way. So usually you overdo it and then you regularize too much, and hence you lose performance. Okay, so this is why this was an iterative process. So weak convexity, what is it and why is it interesting? So just as a reminder, so a function is called weakly convex, or row weakly convex in particular, if you can add a quadratic to this function multiplied by rho, and you can turn it into a convex function. This is a very wide class of functions, which is why it's good, but it has still enough structure for certain things that we want to do. How can we impose weak convexity in a neural network form? We can use this characterization of weakly convex function, which says that weakly convex functions can be represented by a composition of a convex function and a smooth function. And for both, we have neural network parameterizations that we can just fall back on. So there is something for convexity, there is something that is called input convex neural networks, ICNNs that we can use for the convex part, and smooth, you just use smooth nonlinearities in your parameterization of the neural network, smooth activation functions. Why is weak convexity nice? It's still general enough to be able to approximate quite a wide range of possible regularizers, which this density argument should demonstrate. And also, once you plug it back into your variational problem, you can prove you can prove existence, you can prove stability properties, although weak stability properties, and you can also devise optimization algorithms that have convergence properties for this variational problem that in the end you're solving. Let me jump this. This is basically what I just said. You can prove some well-postness, existence. You can prove also something that in inverse problems people are very keen on, which is called proving that the regularization is convergent. But I can tell you more if you're interested. It doesn't need to. So this is basically what I've just said. Let me jump that. So now how does it work? This is now this X-ray CT example on an openly available data set from the Mayo Clinic. And I'm using it in this underdetermined and noisy case. So you have undersampled measurements and they're noisy. What you see here are the reconstructions that I'm going to show you. So I'm going to show you the pseudo-inverse reconstruction, so the filtered back projection reconstruction, total variation regularization reconstruction, the weakly adversarial convex regularizer reconstruction, which is called AWCR, and then compare it with, I would say, the nowadays gold standard for deeply learned approaches for solving inverse problems, which is called learned primal dual, which in comparison with the AWCR, with our learning the regularizer strategy, is very different because the neural network itself solves the inverse problem. It's completely supervised, so meaning that you have paired data, and you don't have mathematical guarantees, basically. At least not in the practical setting. Now, how does it look? So this is now the reconstructions you see here on the right, in comparison with what I call here the ground truth. So this is the fully sampled, low noise reconstructions that have been clinically that just come out of the computed tomography machine. And the numbers here on the bottom are are a quantification of how well you're matching, how well this reconstruction matches this ground truth image. The higher they are, the better. So this is what is called the PSNR, the peak signal to noise ratio. And this is the structural similarity index measured, the SSIM, which is a bit of a refined version of evaluating the quality of this reconstruction. Okay, with quality I mean again how close it is to this ground truth. This is total variation regularization. Okay, so you can see here filtered back from pseudo-inverse doesn't do much regularization. Total variation definitely does. Maybe overdoes it. Yeah, so maybe is overdoing it in some parts. But interestingly enough, is always this also thing with these quantifications of how good reconstructions are. These values are much higher than for filter back projection. This is what you get with this adversarial learned regularizer. So you get definitely much more details than you have with total variation regularization, and still get rid of the noise. By the way, getting rid of the noise is not just a visual thing, not just important for visual purposes, but it's important because you later want to do something with the image. And noise is a nuisance for quantifying things on images or segmenting images or something like this. So it's a robustness issue that you have with the noise. That's why you want to get rid of it. And this is what you get with learned primal dual. So they're very close. So this is this gold standard deep learning reconstruction. They're very close. The difference really is for one you have some mathematical guarantees and structure, for the other one you don't. Okay, now I'm going to jump. I had some more things here, but this was too optimistic. Let me say just a few more words about the other way around, so imposing structure directly in the neural network that is now, solving in our case again the inverse problem. And here I would say the most successful looking glass, or the most successful way to impose structure into neural networks from an analysis viewpoint in the last years has been this dynamical systems PDE-ODE lens onto neural networks. So thinking about neural networks as discretizations of dynamical systems of differential equations. Okay, and hence imposing something onto these neural networks via this analogy. So, you know, if you're more from a numerical analysis background, our entry point, and I think this is really the right way to look at this, is really via this subfield of numerical analysis that is called geometric integration, where you have a continuous model that you know has certain properties, and you want to devise numerical solutions, so discretizations of this continuous model that preserve this structure, these certain properties. Okay, and now you can do a similar thing, but just make a neural network out of this game. And the one thing we did was here in the context of one Lipschitz and alpha averaged network. So what is it? The idea here is the connection between dynamical systems and neural networks really is via so-called residual neural networks. Residual neural networks are networks that are a composition of so-called residual blocks of functions that start with the output of the previous function, so of the previous layer, right? Each of these functions you can think of as a layer in a neural network, and add a modification of this input by some linear term, so multiplication with a matrix, and some pointwise nonlinearity that is the sigma here, which is also called the activation function. Now, if you look at this, you can, so this is again just writing this up here, you can also interpret this very easily as just one explicit Euler step of an initial value problem like this, right, with step size 1. And then the neural network is basically just capital L such explicit Euler steps. Now, this is one direction, but now you can take the other direction, right? You can start with a dynamical system, again, that might have certain properties that you want your neural network to have. You choose a numerical method that preserves this property. Here again, just using explicit Euler, just for demonstration issues. You can change also the step size here, right? You can just have h, for instance, as a step size, and then you make a neural network out of this. And so like this, you can design different types of neural networks. For instance, you can design neural networks that are volume preserving. And this goes like this. So you have now a dynamical system that looks like this. And I'm already writing it like this because the numerical scheme that I will devise to preserve the volume preserving property of this neural network will be a splitting approach. So the idea is you choose the dynamical system and the associated numerical scheme that preserves the property, in our case volume preservation, and you make a neural network out of it. So now we did this, as I said, for one Lipschitz and alpha averaged neural networks. And I'll just, I think I'll more or less need to jump that, but the idea is just coming out of what I've said before. By the way, one Lipschitzness makes sense because you have some continuity in the neural network. You can have a tuning that makes the neural network robust to perturbations. And the alpha averaging is an extension of this one Lipschitzness when you are in the situation when you want to use a neural network to compute a fixed point. Okay, if you really want convergence to a fixed point, if you go through the layers of your neural network, alpha averaging gives you a sufficient condition to get this convergence. Okay, so I think I'll jump that, but you can do this in a similar way as before. In the case of one Lipschitz and alpha averaging, if you stick to explicit Euler schemes to make up your neural network, it will result in a restriction onto your step sizes in this explicit Euler scheme to get the one Lipschitz or the alpha averaging property. But let me jump to the end. So right, so now what I've talked about are two, let me go to this one first. So overall takeaway messages, what I've talked about is the appearance of structure in neural networks, in particular when we encounter neural networks in the context of inverse problems, and also when we use structure to impose certain properties on neural networks, maybe for more general purposes like making them more robust. There are these two paths, so you can use deep learning and put deep learning into a mathematical model, and the other way around, put mathematics into neural networks. And there were some overall challenges that we encountered while talking about this. One is this trade-off between structure and expressivity, which is very tightly linked to our ability to model this structure in an efficient and accurate way. So something that I didn't talk about, and this is a really big topic within structure preservation, is using deep learning for solving PDEs. Here different things could happen. One could be, again, to model neural networks to have certain properties that I know the PDE has if I want to use it as a solver for this PDE. So for instance, to impose on a neural network to have an Hamiltonian structure if I want to use it to solve Hamiltonian systems. And another thing that we recently did, which I thought was very interesting, but I decided not to talk about it because it would consume too much time, is to use things like Lie group symmetries of solutions of PDEs to make neural network solvers for solving these PDEs more generalizable by using the symmetry as a way to generalize PDE solvers trained on a particular type of training data, particular type of initial conditions, to initial conditions that haven't been seen by using this Lie group symmetry. Okay, so I think with that I'll finish, and I'll thank you all very much for your attention.
Thank you very much for your wonderful talk. Are there questions? Please.
Thank you very much for a very interesting talk. So, in the very end, in the very beginning, you mentioned the solving PDEs with machine learning, and in our field, in turbulence, when you solve Navier-Stokes with high Reynolds numbers, we need to make closure models, and closure models are intrinsically stochastic. So there is stochasticity physical part. So in a sense, opposite to the usual point of view, when you always have a noise and get rid of it, the stochastic part is essentially what we need to reconstruct. So the problem we have is how to learn and reproduce stochastic process, let's say Markov process, to make it concrete. And I really don't see any other way how to do it practically, if not with machine learning. So what do you know about this method? So you have a data which you know is a Markov process. You want that your system understands what is this process and just reproduce. So I give you the state, you give me the state which corresponds to the distribution, to the law.
So I haven't looked at the specific example myself, but more generally I would say the same applies that I said before. If you can represent these stochastic processes, if they are constrained enough, so you can actually represent them faithfully through finite dimensional training data, then you have a chance that this works. Or, and maybe, both together would even be better, you have some way to formalize what you know about your Markov property in terms of something you put into either the neural network. By the way, I mainly talked about imposing structure in the neural network itself, but you can also impose structure in the loss function, right? This is also what some people are doing. So ideally, if you want something that is generalizable, use as much prior knowledge as you have to still impose that into your neural network training, and really think how you can represent the distribution of your stochastic processes in terms of a training data set. That's really the main challenge.
Yeah, because we try to do different groups, so the idea is relatively clear theoretically, but practically it's very complicated, especially the dimension is very large, so you cannot really reproduce distribution. Distribution somehow has to be part of the neural network. So do you know if there is this direction is developed now? Or?
I don't know.
No.
I don't know in this particular case.
Thank
but
you.
Again, just pointing towards this example with the canonicalization, maybe you can't represent all your solutions. Maybe you can't represent the solutions to all of your, you can't represent all of the stochastic processes happening in your distribution, but maybe you have some underlying symmetry, like in the case of PDEs, or something like this that you can use to feed in addition into the process to expand upon your training data. Yeah.
Thank you very much. Unfortunately, we have to continue, so therefore I would like to ask you if you have any more questions and if you want to have nicer discussions, that you do it in the coffee break or later during the day. I mean, use the opportunity. She is here the whole day. So thank you very much for your wonderful talk.
Thank you.
Okay. Now, where's Michael? So let us exchange now the speaker. Well, part of our conference is also a public lecture, which will be given by Professor Michael Różański, who, at least for the persons from the Isaac community, is more than well known. Everybody has seen him already several times. He made his PhD under Distamat and later on became professor at the Imperial College. Now he switched to Ghent University, where he is the head of the Intercontinental PDE and Analysis Center. He has a recipient of the Isaac Award and also the recipient of several large grants like the Odysseus Grant, Methuselah Grant, and so on. So as a researcher, he is a very rich man. Furthermore, as many persons here in the audience can say, he has close contacts with Kazakhstan, and he is first and foremost also for a large part of our community a very good friend. So let's welcome Michael Różański.
As a pointer, which one?
Just one button.
Okay.
And this is for switching.
Yeah. Okay, so thank you very much for this nice introduction and now I hope it's okay. It's okay, yes, thank you. It's a pleasure for me to be here, and it's not indeed my first visit to Kazakhstan. I have been working with mathematicians from Kazakhstan, and it is a public, I was asked to give a public lecture and to talk a little bit about my experience of working with mathematicians in Kazakhstan. So this is, my lecture will be not partly mathematical, but partly also about this second aspect. And I haven't checked how much time do I actually have. 50 minutes. An hour? 50 minutes? Okay, so this should be okay. And yes, so I singled out as a topic analysis on groups. I put in the announced title homogeneous groups, but then I decided to extend it a bit, collaboration with Kazakhstan, and I have also, I will mention other topics that I worked with, that I worked on with, in collaboration with mathematicians in Kazakhstan. So this is the plan of my talk. So I will first give some motivation, general motivation, working on groups, and from the point of view of function inequalities, and my original interest was the theory of pseudo-differential operators. Then, of course, once we have these methods, we can look at PDEs, where it's natural to consider sub-Laplacian instead of Laplacian, or more generally Hermann's sums of squares, satisfying Hermann's bracket condition, so that operator is sub-elliptic, hyperelliptic, and related topics. So in this talk, I decided to cite mostly or almost exclusively references with mathematicians in Kazakhstan, because we are here in Kazakhstan, and this is the topic of it's a public lecture, not a research lecture. So this is my interest originally, so a little bit of preliminary. My interest before I was coming to Kazakhstan was in analysis on groups, namely pseudo-differential analysis. Of course, we all know the theory of pseudo-differential operators is very effective. It led in particular to many advances. One remarkable is Atiyah-Zinger index theorem on manifolds, which requires a principal symbol of an operator, which is the main part of an operator. But a drawback of Hermann theory is that geometrically on the manifold only the principal part is defined geometrically. It can be thought of as a function or a density on a cotangent bundle of a manifold, but lower order terms, all lower order terms are lost. Geometric information is lost. So it works well like problems like index theorem, which depends only on the principal part of operator, but doesn't work so well problems with low-order terms. So the idea a while ago was to look at situations where we have some additional structure, for example, a Lie group or a manifold with a Lie group acting on it. There are really many of such objects. And use a Fourier analysis which is adapted to the group structure, so work with representations rather than work in local coordinates charts. And this led to these books, which one is with Ville Turunen from Helsinki about developing global theory of pseudo-differential operators and compact Lie groups. And then the other one with my postdoc at the time, Veronique Fischer, which was similar for nilpotent Lie groups. So we developed many techniques, mainly with the aim of dealing with pseudo-differential operators. And then I want to relate this to my collaboration. So that work was independent of Kazakhstan, but then my acquaintance with mathematics in Kazakhstan started from when I attended in 2009. I went to Al-Khwarizmi conference in Uzbekistan, and this was the first time when I met mathematicians from Kazakhstan, Professor Kalmenov, other people, Kanat Shakenov, and so on. And so then 2010, as I checked the as I checked the timeline, it seems that I came first to Kazakhstan in 2010, which is actually interesting because it's 15 years of Nazarbayev University, so I came here also 15 years ago, so I guess exactly at the time when Nazarbayev University was founded. And at that time I gave some lectures at Kazakh National University in Almaty, and then I made a few more visits, and I make lectures mostly on the topic of these books. Well, the first book was appearing at that time, was written already, about pseudo-differential operators, about groups, and in the audience there were many interested young mathematicians that asked many questions, and somehow this led to some collaboration. So 2015 was the first PhD student, Niyaz Takhmagambetov, now actually a professor in Kazakhstan, defended 2015. Then also 2015, Durvudkhan Suragan came as a postdoc. At that time I was at Imperial College, indeed. 2016 also Niyaz and Gulzat Narjubayeva came as postdocs. In 2018 I had another PhD student. These were students funded by the Bolashak program of Kazakhstan. So Rowan Akljanov, who then also became postdoc. And 2020, this was when I was about leaving Imperial College, then also Nurgisa Isirkigenov got his PhD. So this was the beginning, and some of these works I'm going to present in this talk. And then altogether there were quite many over the years. There were many PhD students. So I think some problem, no? There were quite many PhD students. I put them here. I looked in the list. These are only mentioned from Kazakhstan, but all of them are from Kazakhstan. The last three are now currently Yergen Aykin, Yerkin Shemerdenov, Gulnur Zaur. These are current PhD students, but others have defended already. And also in Ghent University, there were quite many postdocs so that I worked with. And so you see the collaboration, at least from this slide, that cooperation with Kazakhstan is quite extensive. And fortunately, in Belgium, I had large grants. Well, still have, so then it allows to having many postdocs. Okay, so this is situation, but now a little bit to mathematics. So the new motivation after this works on pseudo-differential operators, the new motivation came from very simple thing, Hardy inequality. And to remind you, this is a very old topic, of course, and on Rn, it's an inequality which can be, so Hardy original result was in one dimension, was in the integral form, and a little bit different, but equivalent to this one, which I formulate here for simplicity. In Rn, it's an inequality which allows us to estimate weighted L2 norm by the gradient, and of course, we all know that Hardy disliked applied mathematics a lot, but here this result actually has its applications to a lot to mathematical physics, because we have like Coulomb potentials, then it is exactly of this form. And the constant is known to be sharp, so this is classical Hardy inequality in L2, and then later also a version of it exists in LP. And again, so here is two questions usually one studies, the inequality itself, but also the constant, because the constant in the works of Lieb, for example, the constant here is related to the stability of matter, to the mass of electrons, so it has precise physical meaning. And the groups, I mentioned groups, so just a few slides about groups. There are several classes of groups, but so Lie group is a manifold which has a group structure, which is smooth operations of the group. And then it has a Lie algebra, and the algebra is a linear space, and it has a commutator structure, and it's called graded group if it has this the commutator. So if it has decomposition into finite sum, so we talk about, so in this case, nilpotent groups, so it's a finite decomposition, finite remaining commutators are non-zero, and it has this so-called gradation structure that commutator of these two is contained here. So this is a class of groups, and abelian group, abelian Rn, is a trivial example of this graded group. Heisenberg group, when we have two components, this is another example. So there are, and of course there are many more. So this is a graded group. Stratified group is the one where the first stratum G1 generates everything through commutators. So this is, in this case we have sub-Laplacian. We just take a basis of vector fields in the first stratum, sums of its squares, generates the whole Lie algebra. So by Hermander sum of square theorem, sum of squares of this operator is sub-Laplacian, is hyperelliptic. And on these groups there have been also a lot of work. One of the very first and fundamental works was by Folland, who studied these groups, and in particular sub-Laplacian, which is sum of squares, has a fundamental solution. And then the Hardy inequalities, so people looked at Hardy inequalities now if you're on a group. What is the question is, what is a norm that we take as a weight? But for example, one can take this fundamental solution. This is one possibility. So already, if we are on a group, we have two options. We have, because we have different weights, and they give different constants. So if you put fundamental solution of the sub-Laplacian here, we get the constant 2 over q minus 2, where q is homogeneous dimension of the group. But also, and this was the work started with Suragan, that if you put Euclidean norm of the coordinates on the first stratum, then we also have this inequality, but with a different Hardy constant, where n is the dimension of the first stratum. So you see there are different inequalities and different, which are quite different because the constants that we get, best constants, are also different. And then there are also LP versions of this. Again, if we put fundamental solution of the sub-Laplacian, it's homogeneous dimensions appearing here. If you put the Euclidean norm of the first stratum, then it is a dimension of the first stratum which appears as a constant. And so this is one thing on Hardy inequality, but then there was another one, another direction, which is also somehow, maybe I can refer to this paper by Chiati, Cowling, and Ricci, where they have, so all norms, all homogeneous norms to say are equivalent in this situation, but of course the constant depends on which norm we take, but they prove the Hardy inequality itself without constant, where they put the power of sublaplacian. So this is another way, because here we put the gradient, the first order, here we put powers, fractional powers of sublaplacian, so this kind of Hardy inequality is also possible. And again, having seen this, one of the interests was to put other operators here, and also maybe put different indices P and Q in this estimate. So then the question is the following. Then when we are, so you saw that on stratified groups there was quite a lot of works. We can put different weights, and we get different constants. We can work with sublaplacian, but what if the group is not stratified? Then we have different situations. Here I try to explain it in words. So it may still be, it is a graded group, for example, which I gave the definition. It's similar to stratified group, but just the first stratum does not generate the whole group. And then we don't have sublaplacian, but we have high order hyperelliptic operators, so-called Rockland operators. And then we can try to work with these operators instead of sublaplacian. We do not have, but the question is, do they have fundamental solutions? This is one question, because you saw in the weights we put, in one case we put fundamental solution of sublaplacian, but if you have high order operators, then does it have fundamental solution? Good fundamental solution, homogeneous, not always. The answer is, so this is one problem. And another problem is, I also showed this horizontal, so-called horizontal estimate when we put the length of the vector in the first, corresponding to the first stratum, but here there is no first stratum if we are not on a stratified group. So again, a question already, what kind of weight to put and what are fundamental solutions? So the question is even very basic, how to formulate Hardy inequality in two situations. If it's homogeneous group, which is non-graded, so we don't have differential we don't have nice homogeneous differential operators in general. How to formulate Hardy inequality? And the second, if it is graded but not stratified, so we don't have sublaplacian. And these two questions, so over the years, they led to two works. One is, these are people I already mentioned, Kazakhstan colleagues I mentioned already in the previous list. So one was book which was with Suragan, appeared 2019. This is Hardy inequalities on homogeneous groups. Not only Hardy, there are different inequalities in this book. And another one which is, I hope, close to should be close to completion, is with Yeserkigenov, Nurgisa, whom I mentioned, which is devoted to graded but non-stratified groups. Okay, so, and let me just remind you, it's a lot of groups coming quickly, but homogeneous groups may sound difficult, but basically it's just Rn. It's always, we can give abstract definition, but then we can show it's always Rn with a group law which is polynomial. So it's a group which has a dilation structure and which has a group law which is always polynomial, which interacts nicely with a dilation structure. One can think anisotropic or Rn, and so you saw example. Rn is the usual one, is just the group law is linear. Heisenberg group, the group law is quadratic, but all homogeneous groups are like this. So, so we say that there is dilation structure like this, and it is an automorphism of the group. So it interacts nicely, it preserves the group structure. We can take dilations out. group composition law. And so if you fix a basis of the Lie algebra, we can always fix a basis with vector fields which are homogeneous of these degrees. Then the homogeneous dimension is the sum of these degrees in this decomposition, in this dilation structure. So, and these are actually homogeneous groups. It's rather large class because it's almost all nilpotent Lie groups allow for this homogeneous structure. Examples which of when we don't have this structure, homogeneous structures, when we cannot put any homogeneous structures, they are quite artificial, difficult to find. This 9-dimensional is a simple example, but the simplest example. But so all these examples are homogeneous groups. So these groups have been studied extensively. I mentioned the paper of Folland on stratified groups, but then general homogeneous groups is this book by Folland and Stein, where they actually formulated nice philosophy for harmonic analysis. They said it's interesting to find results of harmonic analysis which depend only on the group structure and dilation structure, so that do not require any special information from Euclidean space or Heisenberg group, or somehow they argue that the most beautiful results of harmonic analysis, they depend on the group structure and dilation structure. So that's why they developed this theory of homogeneous groups and Hardy spaces, not Hardy inequalities, but Hardy spaces on those groups. And then, so as I mentioned, I was interested in pseudo-differential theory in this book on such groups, and also this work, Hardy inequalities. Okay, so now somehow historically, so my work, as I mentioned, Durvudhan Suragan came in 2015 as a postdoc, and then somehow this coincided with my interest in groups which was developing, and then it was this question, how to formulate Hardy inequalities on homogeneous groups where we don't have homogeneous differential, nice differential operator. The gradient is not homogeneous. The gradient has, because of the anisotropic structure, in different directions, it has different degree of homogeneity. So if you just put the gradient there in the Hardy inequality, it will not scale well, and then you will not have inequality. So the question is how to formulate. And then we came up with an idea that while we don't have differential operators, but we always have radial derivative. So whatever norm we put, and this results turned out to be new also for Euclidean space, Rn, because we can put different norms. You can put usual L2 norm, you can put taxi cup distance, you can put L infinity norms. These will be all different norms. Balls with respect to these norms are different geometrically. But we can always differentiate in the radial direction with respect to any norm. And this is this radial derivative operator, and it turns out that inequality, if you put this radial derivative here, and I will give some explanation how it's related to why it is Hardy inequality. But if you put this radial direction, then interestingly, for any norm that you consider, or quasi-norm, that you consider, you will get this Hardy inequality with sharp constant, sharp explicit constant. And also Rayleigh inequality, this is the usual inequality when we put x squared here, and here we should have Laplacian on Rn. So this is first order derivative. On Rn, this would be Laplacian. You see here, this is the radial part of the Laplacian. So we have this inequality. And so this was kind of beginning of this investigations, which led to many developments. So the idea was to work consistently with radial derivative, and also when we multiply it by x, this is the Euler operator, which somehow appears in the definition of homogeneous. If you have homogeneous function, it should satisfy Euler equation with a constant, which is degree of homogeneity. And so then here some papers came. So again, it is a public talk, so I will not give you proofs, but just a general overview of my works, especially with Kazakhstan mathematicians. So this was work with Suragan. So we studied, so with this idea, we studied many things, like uncertainty principles on nilpotent Lie groups, weighted inequalities, Caffarelli on Nirenberg inequalities. We introduced, so also Nurgasayer Serkegenov, we introduced function spaces on homogeneous groups. We extended this to exponential weights in this paper. We studied stability of hard inequalities. The question of stability is when we try to estimate the remainder term. Stability. So here was a paper with Ozawa, whom I think I have missed in this Congress, but where ideas of identities and Euclidean space came actually from the works of Ozawa. So this is LP version of Caffarelli-Kohn-Nirenberg inequality and critical inequalities. So all these works I want to mention. So the work on hard inequality started at that time and continues. Now not so active because it's exhausted a little bit, but here we worked on these things and continuing. So this is, but still, so there are some logarithmic inequalities and applications to some PDEs. Aydin Kasimov here. Then P sublaplacians, Bolas Sabitbek, which was in the list of my PhD students, which I co-supervised also. So reverse inequalities. So you can put inequalities in these directions when P is bigger than 1, but if the exponent P and Q are bigger than 1, you have hard inequality, but if they're less than 1, actually you have inequality in the other direction. So these are called reverse inequalities. So recently it was also Morris spaces. So this is kind of Hardy Littlewood Sobolev and its weighted version Stein-Weiss inequality on Morris spaces with Kasimov, Raguza, and then some multidimensional versions because Frank, Laptev, Weil, they introduced some improvement of hard inequality in 1 dimension, and this was extended to n dimensions. Also with, so this is myself and Suragan, plus some other co-authors here. Here I said these are papers with Suragan, so I don't mention Suragan is in all these papers. And then also more recent one, this fractional hard inequalities. So when you have fractional, because on homogeneous groups you also have fractional Laplacian or sublaplacian or p-Laplacian, has different names than in this case Q less than SP, which was not studied before. So all these works were about inequalities and one. So how one gets these inequalities? Just a quick idea. In fact, one way, there are different ways, but one way to get it is through identities. In fact, we have this precise identity, which is very remarkable. So we have this function IP and we have this identity. And the thing is that this expression here is non-negative. If you prove this identity, then you observe that this equality, this part is always larger or equal than 0. And from this, you get that this left-hand side is larger or equal than 0. And this gives exactly the hard inequality. So this identity, here we have identity, but it implies inequality. So this is inequality. It implies different inequalities. So this is called so-called Sobolev type inequality, because here we have derivative. We have, well, here we estimate not function with the weight, we estimate the function itself. So this is called Sobolev type inequality. And usually in Sobolev inequalities, you have different P and Q. But here you can prove that you have to have P equal to Q. So this equality, and then in the, so it can explicitly be written in this way. So you estimate function by derivative with x. with a sharp constant. So this is Sobolev type inequalities that you get from those identities. So from identities you get Sobolev type inequalities, and from Sobolev type inequalities you get Hardy inequalities. So here is the theorem. This is Sobolev type inequality. But if p is equal to 2, so in 2 cases, in fact, this Sobolev type inequality is equivalent to Hardy inequality. And again, we track the constant. And for other p, it is stronger, so it implies the Hardy inequality. So these identities are actually very powerful. They're nice by itself. It's surprising one can get them. And they imply Sobolev type inequalities, which in turn imply Hardy inequalities. Okay, so there are more identities. I will not show you, I will not want to frighten anyone, but okay, some people like it. So there are higher order identities. When we put higher order radial derivatives, then we have all these identities. And again, this is non-negative, so we get higher order. From this we get weighted inequality, and from this we get higher order inequality. So these identities give us inequalities. So in particular, Rayleigh identity. This is Rayleigh identity, and we neglect parts which are non-negative. Then we get Rayleigh inequality. So f divided by x squared, estimated by the radial part of the Laplacian. Here, of course, we don't have any Laplacian. We just take radial part, and then the constant is sharp. So that's how one can deal with these inequalities. And then ideas apply also for critical cases. Critical cases, because you see there are some alpha p is different from q. So if alpha p is equal to q, then this is infinity. This inequality is meaningless. But if you want to get meaningful inequalities, then we have to put log term. We put log term. So this was the work with Suragan, but the works continued. This paper just appeared just, I think, this month. It's some cylindrical extensions of these inequalities. So we have, one can have Yerkin Shemerdyanov is a PhD student. One can have these inequalities high order with logarithmic terms. One can have a lot of inequalities, and there are a lot of interesting things appear in these inequalities as constant Stirling numbers of different types, oblong numbers, and so on. Okay, and one can look at fractional orders. So this with Euler operator, this operator is, we make it self-adjoint Euler operator. It's so-called Komatsu non-negative. It means one can show it satisfies this resolvent estimate. And if it satisfies this resolvent estimate, then the whole theory here of fractional operators works. So we can consider fractional powers of the modulus of Euler operator. And then we can do more inequalities with this. So here is an example of this fractional inequality. And again, we can calculate the constant and so on. So there are many inequalities possible in this setting. So here the book with Suragan, just I mentioned. So all this led to the book which had all these inequalities which I mentioned, but more things, this P-sub-Laplacians, relation to fundamental solutions, different types of uncertainty relations, different types of function spaces on homogeneous groups, potential theory, and also something about sum of squares. So this was kind of summarizing the work that we have done in that direction. So here is this book with Suragan. And here I can mention another book which I wrote with mathematicians in Kazakhstan, which is also Suragan, Durut Khan and Mahmoud Sadebekov. Mahmoud Sadebekov. This is about spectral geometry of partial differential equations. And now I have to speed up, I think. This is both are open access, actually. You can, if one is interested, one can just download them for free. It's open access sign mark here. So spectral geometry. So what it is about here, I just put very quickly to make a. Now I come to the survey part of my lecture, where I just survey different works which I had with all these works with involve at least one co-author from all the papers mentioned involve at least one co-author from Kazakhstan. And so spectral geometry, just to say a few words, this is example. If you have an operator like this is in 2 dimensions. This is the logarithmic potential operator because we have logarithmic fundamental solution. And the question is, basic question, what is over the domain omega? And this is very classical question, for which omega we can maximize or minimize different quantities for this operator. And of course, first eigenvalue, second eigenvalue have been studied. But at that time when Suragan was in London, we started looking at Schatten norms. So when the Schatten norm is minimized or maximized, and for this operator, for example, circle, not surprisingly, circle is the one where one achieves the maximum, but also triangle, if you look at the kind of triangular domains with different triangles of different shapes, and equilateral triangle is the one. So then some works like, okay, this is a bit different, but still boundary value problems on, so Rosenblum, Grigory Rosenblum, this was on Rn, but Schatten norms. So people worked on first and second eigenvalue, but we worked on the Schatten norms. So with Rosenblum there was a paper. Then we looked at this first, second eigenvalue of Riesz transform in spherical hyperbolic geometries because we use rearrangement techniques, and on groups it's harder. We don't have rearrangement techniques, but on spheres, on hyperbolic spaces we have. So then this paper was about some boundary value, layer potential, so potential theory on groups, Garofola. So for in some Heisenberg type groups, comparison principle for nonlinear Rockland operators with Suragan, Kalmenov, Denisbek Sharipovich here, volume potential for the Helmholtz equation, Sabitbek, because we don't, P sublaplacian nonlinear, so we can talk about eigenvalue, but it's principal frequency, so-called. So all these works related to spectral geometry. And then I come, I have to really speed up, I come to the second part, which I said works with Nurgesaya-Serkegenov related hard inequalities. When we don't have the Laplace, sub-Laplacian, we have Rockland operator. And this was the work by, as I mentioned, Ricci, Chiatti, Cowling, when they prove this inequality. But the question, what about other operators? So they relied on the proof a lot on the positivity of the heat kernel for the Laplacian. But for Rockland operators, operators of higher orders, we have heat kernel, but it can be complex. So we cannot use many techniques here. So when we looked at this, not much seemed to be known. So Rockland operators, as I said, this is just homogeneous hyperelliptic invariant differential operators, nilpotent Lie groups, high order. Can consider different, even on Rn, could be powers of Laplacian, can be something like this. On the Heisenberg group, so there are plenty of these operators. We can consider these operators on general graded group. In fact, the existence of this Rockland operator is equivalent to the fact that our nilpotent Lie group is graded. Anyway, so the maybe definition not so important. Important is that we have hyperelliptic homogeneous differential operator of high order. And so there is some, there are some conjectures, Rockland conjectures so-called involved with these operators. Helfer-Nuriga resolved it. It can be this condition, Rockland condition can be expressed as an injectivity of the symbol in terms of representations of the group and so on. So, and then, so as I said, pseudo-differential operators we developed with, in the book with Fisher. But then, so this comes work with Nurgesaya-Serkegenov, where we proved Hardy type inequalities. In fact, we proved more general. So we put Rockland operator here, and this is, we call it Hardy-Sobolev inequality because, so if there is no weight, B is equal to 0, we just recover Sobolev embedding. And if P is equal to Q, then there is weight. Then we have Hardy inequality, for example, of this type as a consequence. We have Freilich inequality of this type. And if the group is stratified, R is Laplacian, then we recover the result which I mentioned by Chiatti, Cowling, enrich. So this is Sobolev. So this is another direction of work which started, and with mostly with Nurgesaya Serkegenov, we looked at the critical versions of this inequality: Trudinger-Moser, Gagliardov-Nierenberg, Kafarelikon-Nierenberg, as I said, Hardy-Littlewood, Sobolev, Stein-Weiss, other inequalities. So in this paper, also best constants in Sobolev inequality we characterized in terms of ground states of this type of equations, also through some variational method. So one can do many interesting things here. So here is a list of, now I'm just come to the more surveying part. So what other things, interesting things I have done in collaboration with Kazakhstan mathematicians. So question of Fourier multipliers and analysis on groups. So Fourier multipliers, these are many works with Rowan Akaljanov, who was my PhD student, and also Irlan Nursultanov from Astana, where we looked for Fourier multipliers and the Hardy-Littlewood, so different Hardy-Littlewood inequalities, because there are many things in mathematics, especially in harmonic analysis, called Hardy-Littlewood. This is different from Hardy-Littlewood Sobolev inequalities, but anyway, Hardy-Littlewood inequalities, this is analogs of Plancherel theorem, but in LP spaces. If P different from 2, we don't have equality, but we have inequalities. These are called Hardy-Littlewood inequalities. So first on SU2 we did, using a lot of explicit information for SU2. Then we understood we don't need this explicit compact groups, Nursultanov, Tikhonov, these Besov spaces, and other spaces and compact homogeneous manifolds with Sean Majid from Queen Mary universities with some quantum groups. On quantum groups, here homogeneous manifolds, and with Rowan quite many papers, LP multipliers on locally compact groups, Ilya Liefland, re-expansions, some norms of affine group, AX plus B groups, and some more recent results also with Kanat Tulenov, Akhembek. This is about quantum torus, quantum Euclidean space. So this is works with Tulenov. This is Sobolev inequality on quantum Euclidean spaces, this paper, and then this is preprint Hermann de Michelin theorem on non-commutative spaces, meaning quantum groups, and general, let's say, locally compact groups. Okay, so and then some non-harmonic analysis in other directions that I pursued with mathematicians with Kazakhstan. This was, as I said, Nilyas Tokhmagombetov was, so to say, the first students I co-supervised in Kazakhstan, and the aim here was to develop a theory of pseudo-differential operators, but for boundary value problems. Of course, we have a very good Bater-Manuel theory, which, however, similar to Hermanda theory, is local. It's based on micro-local analysis. The aim for us was to develop global theory of pseudo-differential operators based on spectral decompositions of some fixed operator. And this we have done with Nilyas Tokhmagombetov. So mainly this paper, rather long, about 70 pages, where we developed this theory and then we applied it to some Shatton classes, convolution, Boltabek, Ismatovich here, convolutions in Hilbert spaces, which is interesting. One can define convolution in general Hilbert space. There is a so-called conclusion convolution for a particular boundary value problem. And then Torebek, some inverse problems for this, and recently also works about application of these ideas now to manifolds with boundary. Not boundary value problems, but to problems on manifolds with boundary. Another topic which I want to mention is very weak solutions. This is something which unrelated to groups, but was a theory which I've been also working on. And I gave some talks about it before, about how to work with PDEs with very singular coefficients. If you have coefficients which are distributions themselves, for example, we have introduced before with my postdoc at that time, Claudia Garetta, we introduced a notion of very weak solution, which allows to deal with these equations. And then some works continued, again with Takuma Gambetta, we applied to some physical problems, general operators with discrete spectrum, some numerical, Altıbay, Rashvin, some numerical simulations of this, Landau Hamiltonian. Then we linked this to groups, for example, Heisenberg group, Rockland operators gradient Lie group, some acoustic problems, Yesterkigenov to hyperelliptic wave equations, indeed, when we have Rockland operator, again, very weak solutions, and some computational aspects. So there are also another direction of research, apart from groups, which is devoted to this analysis on for PDEs. And it continues. It's a very active topic of research. It continues here. Karimov, Erkin John, here Hadzako, Mariana, some works on very weak solutions for some hyperelliptic equations, Schrödinger, Klein-Gordon heat equations one can do, some Sturm-Liouville operators, Alibek, Yesker Mesoulé, we consider this for Sturm-Liouville operators, and so on. So this is the works, another direction of my joint research with mathematicians in Kazakhstan, is this direction of very weak solutions. And then some inequalities, of course, so here and there one can prove some inequalities. So here was with Yeserkigenov, Ari Laptev, at that time for Grushin, hard inequalities for Grushin vector fields, for some Akharonov-Bohm magnetic fields, Sabitbek, Boris Sabitbek, some Bessel pairs, weighted inequalities, anisotropic inequalities. So here is geometric version when the weight is not just the weight, but the weight is distance to the boundary in hard inequalities. This is called geometric hard inequality. So in some half spaces, for example, convex domains, we can do inequalities, and star-shaped domains. So this is Boris Savitbek is a driving force. So he did his PhD, also postdoc, with me, and co-supervised. So here is some inverse problems. So porous media equations and Klein-Gordon equations, all these things, Bessel pairs and some Riemannian manifolds, so many ideas can be used in these different settings. So these are other works with Kazakhstan mathematicians. There is more. So heat equations. Heat equations, so Khalil Rastrepo, we have this like fractional evolution equations and some. So, Virigbold Torebek here, he was in Ghent. There are a series of papers devoted to heat equations, Fujita exponent, when we have similar heat equation, but with forcing terms, for example. And so, degenerate parabolic equations, Fino. Here, inverse problems, inverse source problems. Turmetov, there is one paper on this kind of fractional elliptic problem. And Kompish, Kononbek, is inverse problem, and works in progress. Now there are several papers on arXiv and very exciting work that I'm now very excited about is Fujita exponent, but for example, this is with Hadzako and Kasimov, Aydin Kasimov. When we consider different things, we consider time-dependent function, but also without group structure. We have Hrbanda sum of squares, Kolmogorov operators, Ornstein-Uhlenberg operators, and so on. So these results, I don't have time to talk about them, unfortunately. And so in general groups, there are several types. So I talked about groups of particular type before, homogeneous, graded, but generally groups possible. Hard inequalities on generally groups possible in this paper with Nurgesai Serkigenov. Generally groups. Hardy inequalities, there is a question. What kind of operator you put, what kind of weight? Very interesting. Then logarithmic versions, log Sobolev, log Hardy, log Rayleigh, Nash inequality, Gross inequality, so on. One on general Lie groups. And also Fujita exponent on general unimodular Lie groups in these papers with Khadzaku, Hasimov, Sirkegenov, so this is, and other works, so some, when we have non-unimodular case, sublaplacian with drifts, some factorization properties, and remaining manifolds with negative curvature, again, inequalities, and critical versions of these inequalities on graded groups, so this works. Okay, I think I'm finishing now. This is symmetric spaces, so groups I talked about, but symmetric spaces. Hardy inequality is also possible in symmetric spaces here. Vishvesh Kumar, Hasimov, when we have symmetric spaces, non-compact type, and polar decomposition. So more general metric measure spaces. So more general metric measure spaces, these papers allow to, so we understand more and more. Now, before we need some structure, now we don't need any group structure, metric measure space. We can do these inequalities. And so, to conclude, sorry for so many references, but again, I wouldn't give so many references in a mathematical talk, but it is a public lecture, so please accept my apologies. And so, to conclude, I'm happy to have had a chance to working with many mathematicians from Kazakhstan and also from other countries, whom I have not mentioned or cited here, and I'm confident that the work will continue, hopefully, confidently, will continue towards many new and interesting problems. So, thank you for your attention.
Thank you very much for your wonderful presentation of this impressive work of Kazakh mathematicians. And I hope, yes, please.
Michael, first of all, thank you so much for this wonderful public talk, and thank you for coming. We were a bit worried because, well, we was asking, has he arrived or not? So despite your busy schedule, you made it. Thank you so much. And you have been here for like a long time, right? Like a pandemic happened and so on and so forth. Yeah, it was fun to play with these inequalities at Imperial College, and I just remembered the moment I learned something. Could you please return to Rayleigh inequalities, Hardy and Rayleigh on stratified groups, and it must. Oops, okay, it's long, long behind.
Stratified or?
Yeah, stratified. Somewhere radial version. Should be some.
Was it? No.
All right.
Wait,
yeah.
So.
Back. Yes.
I think Rayleigh. Okay, this is Hardy, and this is.
Stratified. Yeah, back.
This is Rayleigh. Yeah.
Far more back, please. Yeah.
This is Rayleigh.
Yes, there's another Rayleigh back in.
For homogeneous. This is for graded.
For stratified back. Yeah. So I just remembered we should be moving to, yes, this one.
Yeah.
So what appears on the right-hand side, if we rewrite it for Euclidean case, then it's just spherical, radial part of Laplacian.
Yes.
But I was learned, I just remembered that, so the coefficient here is exactly the same coefficient which appears in classical Rayleigh inequality. But here indeed it improves classical Rayleigh inequality in Euclidean case, because if we consider, for example, LP norm of f, Laplace f, which is greater than what appears here. So in other words, Rayleigh inequality on the right-hand side we have Laplace f.
Smaller constant.
Yeah, the same constant. The same constant. If you remember, what we learned was that it indeed, in Euclidean case, improves preserving sharp constant, improves the classical Rayleigh inequality, because one can prove that for smooth functions, of course it's true for solar space by density, for smooth functions, Il2, at least I remember, Il2 norm of Laplace of f is greater than Il2 norm of radial part of Laplace of f. So it's indeed sharp improvement of classical Rayleigh inequality.
Yeah, that's how you get, because radial part is always...
Thank you. That's just comment. Sorry.
Radial part is always estimated by the full operator. That's why it's improvement, and also it's improvement in a sense because this is in the denominator, right? And it's larger constant, homogeneous dimension larger than in Euclidean space. It's the same, but usually it's kind of, if you consider more bigger space, you think what kind of constant. This is a better constants, because and this comes from and sharpness, everything you get from this identity. And recently you can also do LP identities. This is the works of, for example, I mentioned Yerkin Nurgisasov. This is the working his PhD. This is LP versions of identities, also with log terms. One can do identities. So this is very interesting.
Yes, and I think there are a lot more interesting things behind, but I also think that the majority of the audience is very eager to have their coffee, and therefore I would suggest we stop here, and I thank again the speaker.
Thank you.
And now you have the coffee break until 11:30, so please enjoy and come back for the closing ceremony of our conference. Yeah.
Okay. Colleagues, friends, please take seat. So, please take seat. We are approaching to the closing ceremony. So it seems, yes, it's already time. We are a bit behind the schedule. So I ask the Dean of School of Science and Humanities at Nazarbayev University, Professor Gonzalo Artelana. Please, the floor is yours.
Good morning, and a very warm welcome again to distinguished speakers and participants. For this entire week, we listened to many exciting talks and had the opportunity to engage in a multitude of inspiring conversations and academic exchanges. The critical mass of quality academics assembled here provided food for thought, inspiration, and hopefully sparked collaborations that will renew and energize your research when you go back home. This legacy will also endure here at Nazarbayev University with our students and our faculty, and for that I sincerely thank you. This past week, Nazarbayev University experienced and lived mathematics in a constant and very vibrant form. As the Dean of the School of Sciences and Humanities here, I always say that while English is our first language at the school, since all our courses are taught in English, mathematics is a second language of the school. Mathematics is an international language that needs no translation. It is made of equations and graphs that every mathematician understands. Mathematics is also the foundation of every other scientific discipline, not only physics or medicine or engineering. More and more, the very large amount of data collected in social data, in social science and humanities, also requires mathematical tools for analysis, as it was eloquently presented by Professor Carola Vivian Shondip this morning. It has indeed been an honor an immense pleasure to host the 15th Congress of ISAC. Our sincere thanks goes to ISAC for entrusting us in the organization of the local organization of such a significant event. Now, as you depart, I trust you are taking with you many positive memories, not only of the scientific sessions, but also of the University of Astana of Kazakhstan. This country has been traditionally known for the hospitality of its people. Nazarbayev University shares the same values. As such, let this be not a goodbye, but see you later, or in Kazakh, Kezeskinshe. We look forward to seeing you again. Have safe travels back home. Thank you very much. I also have some notes of appreciation to our sponsors and contributors to this Congress. So if I may sort of have a representative of Springer with us. Springer is one of the sponsors. Not today? Okay, we'll have a letter of appreciation for them. We also have Calank Group. Calank Group, KC Group has been also a proud sponsor of the event, and I don't know whether we have some representatives of Calank KC. Also, NU Impact Foundation. I don't know whether we have participants from the NU Impact Foundation. Otherwise, we'll keep that for you. And the Institute of Mathematics and Mathematical Model. I don't know whether we have... there we go. Thank you for your participation. It has a great pleasure and
Thank you.
for helping organize it as well.
Maybe this photo is
Hi. Well, this traditional instrumental music is called kui. Performed by traditional Kazakh musical instruments. I saw dombra and svazga, and let's thank our Nazarbayev University Orchestra once again. These are Nazarbayev University, our talented students, and we have one more talented student. Her name is Lamisa. She is a singer. She kindly agreed to perform, to sing. Lamisa, please. The stage is yours. Thank you, Lamisa, for your perfect performance. This song is about Kazakh people. Indeed, the name of this song is Kazakh people. And we continue our closing ceremony. Now I ask the president of ISAC, Professor Uwe Kehle. The stage is yours, please.
Thank you very much. At this time, it's the usual duty of an ISAC president to thank the local organizers, but this time it's not just a duty, but also a pleasure. I think we all enjoyed our time here, and for me it was especially nice to see a country where mathematicians are treated like rock stars. I also enjoyed very much to see so many young faces here and so many young mathematicians, which tells me that we will have a bright future ahead of us, not only here in Kazakhstan, but also at ISAC. And as a token of my appreciation, I prepared also a letter of appreciation to the Dean of the college, so if I can ask him to come on stage. So. Thank you very much. So, again, all the thanks to the local organizers, especially also to all the students and other guys who actually really have the hard work to actually move us around and make sure that everything works and so on. So thank you very much for that one, and I hope we will enjoy the rest of the times, still the afternoon talks, and I hope also all of you can still enjoy a little bit your time here in Kazakhstan. Thank you very much.
Thank you, Uwe. We continue now. I ask to give speech Vice President of Kazakh Mathematical Society, Professor Academician Tınısbek Şaripoğlu Kalmenov. After this speech, we will have a presentation about next ISAC. So next ISAC organizer will be.
Аса қадірлі ИСАК ұжымының төрағасы Уве Койле. Президиум мүшелері, сіздердің осы ИСАК конгрессін 15-ші Қазақстанға өткіземіз деген сенімдеріңізге көп рахмет. Біріншіден. Екіншіден, осы бүгін осы 15-ші конгресс ойдағыдай өтуіне, жақсы өтуіне ИСАК ұжымының көптеген еңбегі сіңді. Мен ойлап едім басында Қазақстанда болғанда олар келе ме екен, математиктер келмес пе екен деп ойладым. Қорықтым бір жағынан. Енді көріп қуанып отырмын. Бәріміз де қуанып отырмыз. ИСАК енді бұлай конгрессте біз шынында көп барып жүрміз ИСАКтың конгрессінде. Мен Қазақстаннан көп адам барады. Көп адам бар өткені Қазақстанда ИСАКты танытқан, ИСАКқа араластырған. Жаңа ғана көрдіңіздер, біздің профессор Михаил Уржанский Қазақстанға, Европаға жаңадан жол ашты. Рахмет Михаил Уржанскийге.
Okay. Dear President of the ISAC community, dear members of this ISAC Presidium, I would like to congratulate on successfully completing 15th ISAC Congress held in Astana and Kazakhstan. And thank you for all of you for believing in this Congress in Kazakhstan. Thank you for believing for Kazakhstan. I would like to congratulate and say thank you for all of you for participating in this Congress. And I would like to thank for the Michael Ruzhansky for the support and for all of the support. Okay.
Конгресс өте керемет мынау ғылыми жағдайда өтті. Конгрестің өзінің традициясы бар еді. Исақтың әрбір конгресте үлкен проблемаларды айтып, оның жолдарын айтатын үлкен жаңа проблемаларды қоятын еді. Осы жолда сондай болды. Мына пленарлық жиындарда, секцияның жиындарында шешілмеген мыңжылдық проблемалар, навес-стокс туралы, шешілген Пуанкарем проблемалар туралы көптеген жұмыстар болды. Екіншіден тағы жақсы шешілмеген перспективасы жоғары проблемалар айтылды. Олардың бәрі өте қызу жиында талқылауды өтті. Бұл өте жоғары ғылыми жағдайда өтті.
Okay, so in the plenary sessions, they were addressed a lot of mathematical problems, like the problems related to the Poincare, and there were a lot of problems were addressed related to the fundamental and applied mathematics. And we will believe that this kind of problems addressed here will be solved and considered and developed in the future.
Әсіресе конгресске жастар көп қатысты, керемет талантты жастар көп екен, көптеген жастар үлкен жақсы докладтармен таныстырды. Бұл біз үшін, әсіресе қазақстандықтар үшін өте пайдалы болды. Ірі әлемдік ғалымдармен жүздесіп, кездесіп, онымен баяндама жасап олардан пікір алысудың өзі бізге үлкен нәрсе еді. Бұл біз үшін өте пайдалы болды. Мен айтайын дегенім, осы традиция менің ойымша жалғаса береді. Жаңа көріп отырыңыздар доклад, Михаил Ружанов докладынан біздің жолымыз тура, жоғары шығып келе жатырмыз, жоғарылай береміз деп ойлаймыз.
We would like to continue the tradition of this ISAC Congress, and also I'm very happy that we have seen a lot of young generations and young researchers participating in the Congress. And we have seen that the researchers are discussing, they're sharing the ideas with each other, which shows the level of this Congress.
Мен тағы айтайын деген, Қазақстан жағынан локалдық дейді, жергілікті ұйымдастырушылар да керемет жақсы жұмыс жасады. Бар болғаны 5 адам, Дорботхан бастаған. Солардың өзі конференцияның түгел жұмысын түгел атқарды, керемет. Оларға да көп рахмет. Мен осылай жақсы ученыйлар, жақсы организатор болады екен, мен соған өзім таңғалып отырмын, қызығып отырмын.
Okay. Well, I would like to thank for the local organizers, Durut Khan Suragan, and he organized this conference just having 5 assistants, and we can see that the conference held in a high level. Thank you.
Менің тілейтінім осында жинаған математиктерге денсаулықтары зор болсын, ғылымда жетістіктері мол болсын, жоғары болсын, орасан болсын. Құдай қаласа кездескенде осы өзіміздің арамыздан проблема, мыңжылдық проблемалар шешіліп, қуанып қарсы алып отырайық. Бәріңізге табыс тілеймін ғылымда.
I wish you health, I wish you success in everything. See you next time, and I hope that next time one of us who are here will solve some of the important mathematical problems, and we will be happy for that. Thank you for joining, and see you.
Jimei University of China. Jimei University will hold the next Congress. First, on behalf of the new organizers of ISAC 2027, I'd like to thank the organizers to make a very successful ISAC 2025. Also, we thank the ISAC board members who gave us a chance to hold the next Congress. our university want to establish a stronger mathematics subject in the near future. So ISAC 2027 will be strongly supported by the universities. This photo is the full screen of our university, Jimei University. It's near the sea, and the new campus is very beautiful. This building is the main building of the Jimei Universities. Some lectures will be held in these buildings, and it's near building. This building is the School of Science at the Jimei University. Jimei University is located in the Xiamen city. You can look at the box. Xiamen city, the yellow map is a Chinese map. Xiamen city is located in the south part of China. It's neighbor of Taiwan. It's also near Japan and South Korea. This is a sea scale of Xiamen city. It's you can look at it. The half part is Xiamen city. I want to talk about the travels. Xiamen city has an international airport. In 2027, the new airport will be used. It's about 30 kilometers from Jimei University. There is also subway from the airport to the city centers. You take taxi from airport to Jimei University. It's about 80 to 100 Chinese yuan. In Xiamen city, we have also two train stations. One is a bullet train station. Is near the Jimei University. We can take a bullet train to arrive in most Chinese cities. You take taxi from bullet train station to Jimei University. Usually is about 30 Chinese yuan. About the hotel in Xiamen. Since Xiamen is a tourist city, it has many nice hotels in near the universities. I think more than 10 from 3-star to 5-star hotels near the university can be selected as the hotel for ISAC Congress. The standard room of 5-star hotel is about 500 to 600 Chinese yuan. It's about 70 to 85 US dollars. Xiamen city, since it's a seaside city, is one of the most beautiful city in China. There are abundant tourist resources in Xiamen cities. Of course, there are some disadvantages in Xiamen, especially in July and August. The Xiamen city is a bit of hot and humid. The temperature is usually between 25 to 30 degrees. Another bad thing is we cannot control the rains in July. I must say that. For others, we have some hotels for students and guests from developing countries. One choice is about we can use student dormitory at Jimei University. In Xiamen City, we also have some hotels about 200 renminbi, about 30 plus USD connect. So it's also easy to live in Xiamen. So welcome all of you to join ISAC 2027 at Jimei University. Thank you. Thank you very much.
Thank you, Professor Oxen Wang, for your presentation. Just to add, yesterday during ISAC board meeting, I also mentioned this. I visited this university last year with my wife. So, beautiful place. So I spent some nice time there. So I very hope we will meet, see each other in Xiamen City in China in 2 years. But now, to close the ceremony, I invite here new and current ISAC officers. Please, Professor Toft.
So, well, one duty we still have to do is, as is tradition at the ISAC congresses, the board of directors will meet, which happened yesterday, and had to elect the new officers. Since this was my second term, by the constitution I will have to step down, so the board had to elect a new president, a new vice president, also a new treasurer. Well, for the new president, they were choosing a person who actually did work a lot for ISAC in the last, one can say, decades, and it's my great pleasure to call here Professor Joachim Toft from Sweden. He actually will become the new president, and I'm pretty sure he will move our society forward in the future. So, I also would like to call directly the new vice president, which in our society will be now a woman. It will be Professor Paula Sergeiras from Portugal. And persons who know ISAC know that the most important job in the ISAC community and of the ISAC officers is not the president or the vice president, but actually the treasurer and secretary. It's my great pleasure to have Irene Sabadini continuing in this job. Please. So, thank you very much, and please.
Thank you very much. Oh, well, before I just start a little bit, I would just to not forget, I will repeat this later on, but thank you very much, the organizers of this wonderful Congress, okay? You performed something very nice and important here, and also you can feel that when you organize things, you can also see that you are doing it by heart, okay? If you come to an event like this and they have really put their soul in it, it becomes something very fantastic and so on, okay? It's of course an honor for me to be elected as a new president. I have been vice president for some time, I think longer than usual because of this corona time actually, so it was somehow difficult to vote. So I have actually 2 different periods of a vice presidentship. But on the other hand, during my time as vice president, I had a real pleasure that all the presidents of ISAC, they have been fantastic as presidents, okay? It started with Luigi Rodino, 2 years with him, and then after that, Professor Reisich, that I also had 2 years with. And one can say that, especially with Reisich, and then later on with Professor Uwe Keller as the president, ISAC had undergo several important changes, okay, becoming a much stronger society than it ever has ever, okay. And it has been an extremely good leadership, and I'm very honored to continue here. But I don't know if I have a chance to be as good president as Professor Uwe Kähler and the presidents before him, okay? But I will do my best. On the other hand, the only chance to make, to be able to rule Isaac in a good way is that you also have the whole team of the officers are strong enough, okay? So fortunately, I have already been working with our Secretary and Treasurer, Irene Sabadino, for 6 years now. And it has just moved so smoothly, I would say. We really interact with each other very well. And she's really doing well for pushing the society. And fortunately, I have now also Paula Sereya, that is, sorry, I'm not still, I know exactly how.
Enough.
Paula, okay. I know very well how writing your name, but to pronounce it in the correct Portuguese way is not always the easiest way for me. But anyway, I have, though we didn't work together so far, Paula here is perhaps, most of you know Paula and Professor and Irene here as a very good mathematicians, and they are for sure, but they are also very good to work with concerning practical things, okay? So I'm very much looking forward for this, and this is actually, it's only thanks to you if I should be able to be a good, fair president or not, okay? So just before we continue my talk here, I would just give a big appreciation both for the former President Uwe Kähler and also for Irene and Paula here, okay? So. I continue, okay? So ISAC is an excellent platform for supporting analysis, its applications and computations. And we try to be as good support in different contexts of these, within these frames, okay, and these fields, subjects, etc. And also what was important that we were more focusing during the past years, it is about the young scientists. ISAC, I think one of the reasons why ISAC became more and more successful is that we have been very much focused on, we should really try to make, gather young scientists so they can interact and so on. Not only, and also of course that the interaction between younger and senior scientists is important, but also let's say that we are really trying to focus on, well, we should really be an international society. We should try to really make that people from different parts of the world should meet and be able to interact, okay? And I hope that we could, even though I really hope that we can improve these things in the future. Yes. So, of course, to do this, we had to, again, thank people, okay? Beside my dear collaborators in among the officers, I would also say that ISAC board has been very good, worked very well when we have discussed, and they have helped a lot in the work during the during the years, okay? And but of course, without all the ISAC members, it's of course neither any ISAC officers or board members, okay? So thank you very much for all the members and so on. Your presence and what you are doing here, and also then could gather here to the Congress is fantastic, okay? And now I come back to this a little bit about ISAC congresses, and especially this Congress. I already thank generally about this fantastic event, but as someone said, especially thanks to the really organizers of this event, and also those who makes this general job here, that you can see all these volunteers, etc., what they're doing. Especially, I thank Professor Suragan for this very well-organized conference, okay? So let's bring a good appreciation. Okay, yes, please. Please come up here. Yes, all come up. Suragan as well. Can you, please? Yeah, so please. We can see them all here, okay? So let us not give one applause, but 3 applause to them, okay? Okay. Yeah, so thank you very much for this excellent job that all of you made. But of course, I would say that also thanks to all participants to this Congress. It's also very important. I mean, we can reach people also that are not ISAC members, okay? So especially the success of this Congress is also rely on very good plenary speakers, but also all the nice session speakers, okay? And so that's it, okay? And of course, I am looking forward for the next ISAC Congress with at GMA. I'm sorry for my pronunciation, but GMA University at Xiamen. Okay, it looks very exciting, and I know Professor Wang since a long time. Well, he's very well known to be an excellent mathematician, of course, but also he's also very well in organization. So it will be very nice to come to your university about 2 years. And of course, all those of you who are participants but not ISAC members, you are very welcome to join ISAC in the case that you would like to. Yes. So that was everything for me. It was very nice to see all of you. See you in the future. Hopefully all of you will come to China about 2 years. So thank you very much.